Hi everybody, happy late arrival. I'm going to get us going on free fall. So welcome to the last unit of the semester. You've made it. This unit's all about free fall. Tomorrow we'll listen to some Tom Petty, I promise. But take out your new free fall packet that you got in class on Tuesday. We're going to open up to page 3. So free fall for physics, our definition is going to be it's when an object's in the air and nothing's touching it. So if you're touching it, it's not free fall. But the second it leaves your hand to the second before it hits something else, it's considered in free fall. So pause the video, and what I want you to do is put a check mark next to which of these situations you think would be considered free fall. So pause the video now. All right, let's go over them. So an apple falling towards Sir Isaac Newton's head. Heck yes, that's free fall. The apple is falling and nothing's touching it. It's in the air, nothing's touching it. Second one, a basketball's traveling upwards towards a hoop. Simone, our all-star basketball player, our physics friend, shoots a basketball and it's going up. Is that considered free fall? Yes, physics friends, it is. Remember, our definition is anytime it's not touching anything. So maybe it's moving up right after you've left your hand, or it's moving down like the apple falling down. Both of those are considered free fall. A cannonball is launched and traveling towards the ground in a parabolic path. So that's like a parabola. Is anything touching it? Nope, it's free fall. There you go. A cheerleader is thrown up and momentarily stops at the top of her path. She's not moving. She stops momentarily. Is she in free fall? Heck yes, she is. No one's touching her at that point, okay? You're starting to see the pattern. All of these are free fall. A clumsy student falls down the stairs, not while they're hitting the stairs, but like when they bounce, that would be considered free fall. So yes, free fall can mean on the way up. It can mean on the way down. It could be that moment that you stop at the top of your path. All of those are considered free fall for physics because nothing is touching the object. All right. You should love free fall. You're going to love the unit, I promise, because we're doing the exact same skills we've been practicing all semester with motion that you're already pretty familiar with. You've seen objects be in free fall before. This unit really should act as a semester review. It's going to feel like we've already done this stuff. Awesome. Let's go. All right, so on page 3, let's try it. Let's do forces. So grab an object that's near you, your pen, hopefully not your phone, but something. Hold it out at arm's length and drop it. So I've got my ID. I'm going to hold it, drop it, you drop something. Cool. Now draw a free body diagram for the object after it leaves your hand. Make a claim about what's happening to the speed of the object, and write your forces explanation. Like I said, we've already done this. So pause the video here and try this, and then we'll check in. That's my pause face. You're paused. All right, let's go over it. Here you go. When things are in free fall, the only force acting on them is the force of gravity. We said nothing's touching them, so there can't be any other object exerting a force on them. So nothing in the x direction. F net y is Fg. The velocity's down, and the acceleration and net force are down because the force is down. So what's going to happen to the object's speed? It's going to increase speed. So read this explanation, see if it matches yours, edit yours if needed. All right, we're going to keep going. If you ever need to pause this video, please do so. You should be pausing it a lot. On to page 4 at the top. When an object's in free fall, the only force acting on it is the force of gravity. Since the net force of that object in free fall is pointing down, right, because gravity always points down, then the acceleration must also be pointing down. We learned that in Unit 2. This means that the speed of objects on their way up, so the basketball on its way up, velocity's up, acceleration's down, the speed's going to decrease. That's why when you throw something up in the air, it slows down, because the force of gravity is pulling it down, accelerating it downward. And when it turns around and comes back down, the speed's going to increase, right? Because gravity is speeding it up. The acceleration and the velocity go together, it's speeding up. And then there's this point at the very top of the path that objects turn around and the speed is 0. This is weird because the speed is 0, but their acceleration points down because their net force points down. Weird physics idea that things can be not moving and accelerating. You throw a basketball up in the air. At the very top, it stops, not moving, but it still is accelerating downward. That's why it comes back down. All right. You know what's cooler than force diagrams? Graphs. Let's do them again. All right. So the scenario is a physics student drops a ruler from a height of 1 meter and catches it before it hits the ground. We're going to draw a position time graph for this. Back to Unit 1, position time graphs. Pause the video, see if you can remember. What would the position time graph look like for something like this? All right. It should look like this. Starting at a positive position, moving downward, and getting steeper and steeper and steeper because objects in free fall speed up on their way down. Their velocity increases. They go faster and faster and faster as they head towards the ground. All right, so now pause the video and see if you can answer B, C, and D on page 4, and then we'll go over it. All right, B, you should say initial position's positive because the y-intercept's positive. You always say something about physics because something about the graph. Direction, negative direction because the slope is negative. Part of a graph. Speeding up because the slope is getting steeper as we go on. So you're always saying what's happening to the object because what part of the graph tells me that. All right, now we're going to do a velocity graph. Friends, it's all a review of first semester, okay? What would the velocity graph look like? Pause the video and try it out. It would look like this, okay? Starting at rest, so that should be starting at 0. It looks a little bit below, but it should be at 0. Speeding up in the negative direction, going away from 0. So pause the video again and answer F, G, and H in your packet. All right. F should say the initial velocity is 0 because the y-intercept's 0. G should say negative direction because the line is in the negative quadrant. H should say the ruler is speeding up because the line is moving away from 0. So make sure you've got all of page 4 done. At this point, you can rewind the video if you missed any of those. All right. You know what makes me giggle? LOL diagrams. I know, I'm funny. We can also do free fall with energy. We can analyze it from an energy perspective. So go ahead and try this page. Try page 5, and then I'm going to go through the answers. So pause the video, try this explanation, and then we'll go over it. All right, here's the answer, friends. You've seen this stuff before. So A has more velocity, same mass, so it has more kinetic energy. We're ignoring air resistance unless the problem says there's air resistance, so no work. So it ends with more UG. So here is my explanation. Check yours. Make sure it looks good. Make sure you've got pages 3, 4, and 5 filled out. I'm checking those in tomorrow. And have a wonderful day. I'll see you on Friday.